Welcome to this session, impedance matching in RF circuits. Here we are going to discuss about impedance matching. Normally, the source is connected with the load with the help of transmission line in RF circuits. But the load impedance is not equal to the source impedance. We cannot satisfy maximum power transfer theorem. So loss is there and also amplitude and phase errors are occurred. To avoid this, we are going to introduce a network that is called matching network in between source and load. So it has to increase the maximum power from source to load. So now this circuit has to satisfy maximum power transfer theorem. Now, if you are using lumped components, that is L and C in a circuit, then that circuit is called lumped matching network. Apart from that, if you are using transmission lines or to design a matching network, then that is called distributed matching network. Now, we are going to focus only distributed matching network. In this matching network, we are having two types. One is single step methodology, another one is double step methodology. In a single or double, based on the connections, it may be series or shunt. At the same time, the stubs are in open or short circuited nature. Here we are using the terminology stub. What is that? It is a transmission line. It is used, it is in parallel or series connection, maybe open or short. Series or shunt connection topology is clearly explained in this two diagram. Here, this is a stub. This stub is connected in parallel with the load. Here, this is a stub. This stub is connected in series with the load. Anyway, here the distance D and the length of the stub, these two are the design parameters for a matching network. Now we are going to see shunt stub matching. These are the design steps for obtaining D and L of a network. Now we are going to follow these steps with the help of a problem. The problem is for a load impedance ZL equal to 60 minus J 80 ohm, design two single step short circuit shunt tuning networks to match this load to a 50 ohm line. Assuming that the load is matched at 2 gigahertz and that the load consists of a resistor and capacitor in series. Here the details are ZL that is given, Z0 that is given, and the frequency is given. They are asking two single step matching network and the stubs are connected in shunt and also short circuited. These are the details given in the problem. Based on the design steps, now we are going to plot ZL. For that, we are going to calculate the small ZL. This is the normalized impedance. This normalized impedance is calculated from the given load and the Z0 value. So load divided by Z0, we are getting normalized impedance. That is 60 minus J80 divided by 50 equal to 1.2 minus J 1.6. This value will be plotted on the Smith chart. And then we are going to draw SWR circle. That circle goes through ZL. Again, convert ZL to load admittance YL. Afterwards, the Smith chart acts as an admittance chart. Now, we are going to plot ZL. For that, we are going to identify 1.2 circle. This is the constant resistance circle, 1.2 circle. Again, we are going to identify minus 1.6 circle. So, minus means we are taking the bottom half of the Smith chart, bottom part of the Smith chart and identifying 1.6 circle. Now this 1.2 circle and 1.6 circle, these two are intersecting at this point. So this point is called ZL. So now we plotted the ZL value. The second step is we are going to draw VSWR circle. For this, we are taking the center of the Smith chart, that is the center of our SWR circle, and radius, that is a line connecting center of the Smith chart and ZL. That will make the radius of the circle. Now using this, we are going to draw a SWR circle. So this circle is called SWR circle. Third point, identify YL. That is, we are going to draw a line. That line connects ZL and ZL center and extend the line opposite to ZL that intersect our SWR circle at a particular point, and also extend the line after this intersecting point up to the outermost circle of the Smith chart. Now we are identifying YL. That is the circle and line, these two are intersecting at a point, that is called YL. Now this chart behaves like an admittance chart. The next point is we are going to identify the intersecting points. That is SWR circle and 1 plus JB circle. These two are intersecting at two different locations. One is in the upper part, another one is in the lower part. In the upper part, we marked as a A1. In the lower part, we marked as a A2. Now, we are going to identify the admittance value of these 2 points. That is Y1 equal to 1. That is the constant conductance value 1 plus J 1.55 for the bottom case, 1 minus J 1.55. That is explained here. So Y1 equal to 1 plus J 1.55, Y2 equal to 1 minus J 1.55. Now, the distance between YL to Y1 is called D1, and distance between YL to Y2, that is called D2. We are moving towards generator. We are moving towards generator from YL to A1 point, that will give D1. We are moving towards generator from YL to A2, that will give D2. That is D1 equal to 0.177 lambda minus 0.062 lambda, that is equal to 0.115 lambda, and D2 equal to 0.323 lambda minus 0.062 lambda, that is equal to 0.262 lambda. Here, the first point, A1 point, introduce 0.177 lambda, that will read in the outermost scale. So we read of this value from the outermost scale. So using the outermost scale, the A2 point gives 0.323 lambda and YL point gives 0.062 lambda. So distance between YL to 0.177 lambda, we are getting 0.115 lambda, and distance between YL to, that is 0.062 lambda to 0.323 lambda, that is equal to 0.262 lambda. Now, next point is add shunt admittance to arrive at the center of the Smith chart. That is, add susceptance. to arrive at the center of the Smith chart. It may be either plus J 1.55 or minus J 1.55. For the first case, Y1 case, we are going to add minus J 1.55. So 1 plus J 1.55 minus J 1.55, that is equal to 1. This is the center of the Smith chart value. So minus J 1.55, that will give the solution for the first point. So this minus J 1.55 susceptance value gives 0.34 lambda. Next, point that is plus J 1.55 gives 0.159 lambda. So from these two values, we are calculating L1 and L2. Okay, that is 0.34 lambda minus 0.25 lambda equal to 0.9 lambda. Now, we are going to find the length of the line. Before that, we are going to identify which is our starting point. That is the next step. Start from y equal to infinity because we want short circuit stub. So leftmost point gives open circuit, rightmost point, that is infinity point, gives short circuit. So here we are going to start at the infinity point. So from this point to 0.34, that will give our length L1, stub length L1. Then this point to this 0.159 lambda, that will give the distance, the length L2. That is explained here. That is L1 equal to 0.34 lambda minus 0.25 lambda, because this is the starting point. Instead of 0, we are having 0.25 lambda. So we are subtracting 0.25 lambda equal to 0.9 lambda. Then L2 equal to 0.25 lambda plus 0.159 lambda, that is equal to 0.409 lambda, because instead of this starting point 0 point, we are having 0.25 lambda. So we have to add 0.25 lambda plus 0.159 lambda equal to 0.409 lambda. So here we are calculating D1, D2, L1, L2. Using this, we are going to draw the circuit. That is from load to the stub location, that is D1, that is equal to 0.115 lambda. Then length of the stub is 0.09 lambda. It is a short circuited one. So this end is shorted. This is first solution. Second solution, from load to the location of the stub is D2, that is equal to 0.262 lambda, and length of the stub is 0.409 lambda. So these are the two solutions for this given problem. So I think you have to clearly understand this design of shunt stub. Instead of this short circuited stub, they have given open circuited stub. We have to start from this point. Instead of infinity point, we have to start from this point. So this is our starting point. Okay, so I clearly explained the design of shunt stub matching network.